So welcome to this next lecture. In last couple of lectures we have looked at fluid reactions. We have seen how to calculate rates, how to write rates, and in the last lecture we have seen how to calculate some of these things and how we can use it for problems. In the last problem we saw H2S absorption rate increased because of reaction. Right? Reaction shifted from partly gas side, partly liquid side mass transfer control to completely gas side mass transfer control, because the rate became so high it eliminated the liquid side mass transfer resistance. Right, so this is how we are going to use all these things. Let's continue our discussion further, and let's continue further. This is where we are in the course. We are on part 6, last part of our course, right? We have looked at mass transfer with chemical reaction, regimes and examples. This lecture we are looking at model contactors. In the last lecture we'll look at design aspects of reactors. Just to revise, recall the rate expression for various regimes. If you don't remember, it's okay. Look at the last lecture, last two videos, and see for yourself. These are the rate expressions. What I want you to do is write the dependence of Ra on KL, A bar, epsilon L, A star, B naught, Kmn in different regimes. Make a table, different regimes. How does rate depend on these parameters? There is an important aspect coming from here. Right? So if you write regime 1, regime 2, let's just pause a little bit. Okay, so if you think about this, regime 1. What is regime 1? Look at the previous slide. Oops. Yeah. Regime 1, this is the rate expression. Okay. So in regime 1, rate does not depend on KL, rate does not depend on A bar. Rate depends on epsilon L, proportional to epsilon L. Rate is proportional to Km. Rate is proportional to A star raised to M. Rate is proportional to B naught raised to L. Regime 2 depends on KL, depends on A bar, depends on A star, does not depend on epsilon L, does not depend on Km, does not depend on B naught. Regime 3, regime 4. Question that I want to ask you is, why should we know in what regime reactor is operating? So if you are, say, analyzing performance of a given reactor, then we should know where it is operating, right? Otherwise, how do we improve the performance if I don't know in what regime it is operating? For example, if say it is operating in the regime 2 and we want to improve the performance, you might say it's a reaction happening, let's increase the temperature, rate constant will increase. But if it's in regime 2, it is not at all dependent on rate constant. A star changes little with solubility. In fact, A star may reduce with solubility. KL may increase slightly with solubility because of diffusivity. Okay. So effect of temperature is going to be very weak in regime 2, may even reduce. Right. So our corrective action of increasing temperature to improve the performance may result in fact in a negative performance. It has reduced performance. But if it is in regime 1 or regime 3, then if I increase temperature, rate constant will increase, our reaction will increase, our conversion will improve. Of course, safety, all those things we have to consider, temperature may increase and so on. But dependence of rate on temperature in regime 1 is going to be stronger than in regime 2, because it is only proportional to square root Km. You see? So if I want to improve, if I want to analyze, we should know what regime the reactor is operating, and therefore it is important to know. If I have to know, what should I do? I need to know kinetics of the reaction. Only if I know kinetics of the reaction, I will be able to compare mass transfer rate and kinetic rate and decide what regime it is operating. So now tell me, if I want to measure intrinsic kinetics, should my reactor be operating in regime 1 or regime 2 or regime 3 or regime 4? If you are operating in regime 2 and then you vary the gas phase partial pressure or gas phase or A star, you will find a linear dependence. You might wrongly say that reaction is first order with respect to A and zero order with respect to B. That may not be correct. You will not be able to get Kmn. You are actually getting Kla. You will find it is a very weak function of temperature. That's not correct. So if you have to get measure intrinsic kinetics, you have to operate your reactor either in regime 1 or in regime 3. And look at regime 3. This is like false kinetics that we saw when we were talking about reaction determining kinetics of a solid catalyzed reaction. Diffusion is falsifying the kinetics. So now what equipment we should use? The equipment that we should use allow us to measure KL separately, A separately, and we are also, it should allow us to vary the mass transfer coefficient so that we can come to regime 1 or so that we can come to regime 3. These equipment are called as model contactors. We are going to spend some time on these model contactors. So this is what we have seen. In which regime should the model contactor operate to allow determination of intrinsic kinetics? Regime 1. What characteristics should model contactors have? They should allow determination of KL directly from hydrodynamics. Equipment that does this is called as laminar jet or wetted wall or wetted sphere. They should allow variation of surface area, interfacial area, stirred cell. They should allow variation of operating condition to change KLA. Equipment that model contactor that does this is called as mechanically agitated contactor. We'll see examples of all of this and we'll see how this actually is achieved. Okay. With an increase in KLA, I would like you to plot how RA would vary with KLA. We have done this in the last lecture when we varied KLA. Go back to last lecture if you want. Okay. If KLA is very small, we are in, say, mass transfer control regime. But as I increase the mass transfer resistance, as I increase the mass transfer coefficient, reduce the mass transfer resistance, it slowly shifts to kinetically controlled regime. And then we are in a kinetically controlled regime here. Regime 1. This side, it is all mass transfer control. Regime 2, regime 3, regime 4. Right? This is where we should be measuring kinetics. So I should have an independent way of varying KL and A, and then we can measure the intrinsic kinetics. So anyway, it is drawn for you. Okay. If reaction is in regime 3, we'll get falsified kinetics. Recall. So what information we need from mass laboratory? We need to eliminate all mixing and mass transfer issues. So high RPM. Result should be independent of RPM because KLA depends on RPM. Turbulence and dispersion, interfacial area depends on RPM. We also need kinetics of reaction, means we need rate constant, we need order. That's the intrinsic kinetic. But we also need heats of reaction. Reaction could be exothermic, and we have seen in the early part of our syllabus what happens when heat of reaction is there and how temperature can create problems, how temperature rise can create problems for us. We need solubility, Henry's constant, that allows us to determine A star. We need vapor liquid equilibrium because vapor pressure, solvent may have a vapor pressure. Our B naught our B may vaporize, or solvent may be there that is used to dissolve B, that may have a vapor pressure. So that will decide your partial pressure of A. If it's a liquid-liquid reaction, we need distribution coefficients, right? So these are the things that we need from laboratory. Let's not worry too much about this just now. Using this information now, equipment can be designed for batch and continuous plants and choose whichever is attractive from economics point of view. That's how we have to do our reaction engineering. That's how we have to design reactors. Little bit about model contactor. So laminar jet apparatus, what you have is a jet of liquid in the laminar regime. So this jet is falling, there is a gas phase here, there is a liquid here, liquid that is falling down. So now interfacial area per unit liquid volume is easy to understand. It is the surface area of this jet. So pi dj lj, dj is the diameter of the jet, lj is the length of the jet, and volume is pi by 4 dj square lj. So surface area is a by 4 by dj. Contact time is how much contact is there by the time liquid goes from here to here. It is velocity of the jet, lj divided by velocity of jet. And then it's like a penetration theory, right? Finite amount of contact time between liquid and gas. So using penetration theory, we can calculate KL independently. We don't have to measure KL. If I know diffusivity, I can calculate. It depends on operating flow rate, Vj, it depends on Lj, right? Surface area depends on diameter of the jet. Ra and Rb can be calculated from liquid flow rate. So if I know QL and B in and B out, and let's say partial pressure is here, gas side it is PA. Let's say gas side is not changing much. Yeah, amount of gas absorbed is very small, so PA is almost constant. We can say that. Okay. Then we can calculate RB from here, and RA can be calculated. So now we know RA, we know KL exactly, we know A bar exactly. A star we can vary by changing the partial pressure of A. Then we are in a position to calculate regime and find out Kmn, A star, M and N, and energy of activation. Another possibility is wetted wall column. So you have a liquid that comes in here, overflows, and there is a film of liquid that forms here, overflows, right? And gas goes countercurrently upwards, and liquid is collected at the end. This film is nice and uniform. It is just not appearing uniform because of my drawing. Okay, liquid can be taken out. So QL, liquid flow rate we know, B in we know, QL we know, B out we know. That tells us QL multiplied by B in minus B. That tells us RB. Z we know, so RA can be calculated. Contact time is now between this liquid falling, length of the film we know, velocity in the film we know. Nusselt film theory we have seen in our heat transfer course, in our momentum transfer course. Film theory, recall. If you don't recall any of the things that I am saying, go back, stop and visit your undergraduate lectures, or ask or read books how to determine film velocity, how to determine film thickness for a given flow rate and given wetted area. Contact time can be calculated, mass transfer coefficient can be calculated, interfacial area is known exactly. So that's why they are in the first category. They allow determination of KL directly from operating condition, meaning hydrodynamics, and they allow variation of interfacial area. I can take different lengths of tubes. So here is a problem. There is a laminar jet apparatus used to investigate kinetics of a reaction. Following are the properties: dA, dB, Z is 1, dJ is 1. The table below gives experimental data. Lj is known, QL, Q jet is known, B in is known, A star is known, B percent conversion of B is there given. So B naught can, B out can be calculated. Estimate intrinsic kinetics of the reaction. Do this for yourself. So for each row, find KL, A bar, RB, RA. Complete the table. A bar is 4 by dj, 4000 meter square per meter cube. Complete the table. Do it for yourself. This is how it will look like. Your KL, you check each and every value. You do it yourself. KLA into A star would be 6.24 into 10 raised to minus 3. Right? A star I have told you. RA is this. dB B naught by Z dA star. So what is the regime? KLA is higher than RA. Is there enhancement? No. 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 Well, slight. Oh, here there is an enhancement. Here there is no enhancement. Here some enhancement. So more or less here we are in regime 1 or we are in between regime 1 and 2. How do you proceed to get kinetics? Think about this. Answer is not there. So that's our homework. Next category, stirred cell. So there's a flat gas liquid interface. So imagine that there is a gas here, there is a liquid here. We have some disc here, which is a central hole. This is now our interfacial area. Right? This part. And I can take different discs with central holes and I can gas and liquid phase mixing. We can have a stirrer here, we can also have a stirrer here to eliminate liquid side mass transfer resistance, to eliminate gas side mass transfer resistance, right? Or a mechanically agitated contactor. We agitate this impeller, there is a we rotate this impeller, there is gas here, there is liquid here. Rotation creates dispersion, we create bubbles of liquid, bubbles of gas in the liquid. And as I increase the speed, more and more bubbles will be created. So KL will increase, turbulence will increase, A bar will increase because hold up is increasing, more and more bubbles are formed. So I can increase RPM and then rate will increase because I am eliminating mass transfer. And under this condition now, we have eliminated mass transfer resistance. And then we can estimate kinetics in this regime by changing partial pressure of A, by changing B naught. And see how rate depends on A, PA rate depends on B naught. Then we can get M, N. Do this at different temperatures. Then we'll get energy of activation. Here is a small problem. A cylindrical stirred cell, 5 cm diameter, containing 100 ml of liquid is used to investigate kinetics of reaction. Following are some properties: dA, dB, Z, A star. Table below gives data at different impeller speeds. Speed n equal to 0.5 rps, n equal to 1 rps, n equal to 2 rps. With respect to time, how B naught is reducing. With respect to time, how B naught is reducing. With respect to time, how B naught is reducing. Call what is B naught. B naught is the concentration of B in the liquid phase. Okay, in a separate experiment, the following relationship was obtained between KL and N, as KL equal to 2 into 10 raised to minus 5, N raised to 0.8. How do we proceed to get kinetics? Homework. Solve this for yourself. How does RA vary with RPS? From variation of B naught, we can, with time, we can get initial rate, RB as dB naught by dt. Do that. This will give us RA initial. A bar can be calculated from geometry. Can we calculate from geometry? Yes, stirred cell, 5 cm, stirred cell, 5 cm in diameter, 100 ml liquid. Right? Plot RA versus N or KLA. This is how you will get R N equal to 0.512. Use this expression. Get KL. Get KLA. A star, we know, right? This is from here, Ra initial. What do you think? KLA is higher than Ra. Is there enhancement? No. KLA is higher than Ra. Is there enhancement? No. KLA is higher than Ra. Is there enhancement? No. This is like regime 1. Now somewhere here we can operate our reactor and vary V naught, vary partial pressure of A, get the orders and get rate constant. How do you proceed further? This is homework. So heterogeneous reactions book, Doraiswamy and Sharma's book, volume 2, chapter 2, examples 1 to 5, they are based on these model contactors. Study them. The book also gives solution for some of them. Okay. Study them. That's your homework. So we'll stop this lecture here. We have seen how model contactors can be used to identify regime and then go on to investigate kinetics of the reaction. Why do we need kinetics? Because it is required for scale up. It is required for designing a reactor. Okay, next class we will solve problems on designing reactors where there is gas liquid reaction happening. Okay, that's coming in the next lecture. We'll stop this lecture here.